All right, so I thought I would begin today's class with a practice problem on Hess's law. So you'll see some variation of this on the exam. That's next Saturday. Again, since I'm recording this, let me tell this again. Okay, I moved the exam to next Saturday, and check your Canvas announcements to see all the details. If you have any issues or family or whatever, just email me and talk to me. We'll make arrangements. But your test 3 has been moved. Check your Canvas announcements. All right, today is the 15th of October. Also, lab, this is the last week if you want to do the Hess's Law lab. Okay, so definitely do it. I'll be there. Larissa will be there. And we can get you done in an hour or so with that lab. Okay. All right, so Hess's law, and then we're going to move on to chapter 7. Okay, Hess's law has to do with gymnastics, the gymnastics involving delta H. Okay, what do I mean by gymnastics? Flipping things, turning things upside down, in some cases multiplying. Okay. So here's an example problem. You'll see this in my Canvas videos. The lab report for Hess's law has a huge Hess's law problem. It's like 9-minute video, so it sort of guides you through that. But this is the basic idea that you'll see on a test or an exam. So this is what we're going to call the target. How will we get the delta H of this reaction? Remember, delta H is enthalpy. Okay, enthalpy, which is heat flow. Heat flow. Heat come out, heat come in. It's a heat flow. All right, and if your heat flow is negative, we call that exothermic. If that value is negative, it's exothermic. If it's positive, we call it endothermic. Positive value endothermic, negative value exothermic. All right, so here's how you do this problem. Notice that we have to find the delta H of this, but they gave us 3 reactions here whose delta H we know. All right. Oh, Hazel, sorry, dear. I'm sorry.
Oh, no, it's fine. I was just writing it down. Thank you.
So, what gymnastics can we do here to get to this? Okay, that is what Hess's law is all about. So let's just start here. Let's just label these reactions 1, 2, and 3. Okay, 1 reaction, 2 reaction, and 3 reactions. Okay. All right. Here's how I do it. I'm sure you'll find other people can tell you differently. Just let me tell you how I do it. I look and see what is on the product side. So you see here, I have a 3H2 here. All right. Where do I have a 3H2? I have a 3H2 here, and it's on the product side, so that's good. Okay, I'm not going to change this. Okay, 3H2, 3H2. I'm not going to change anything with reaction number 2. Okay, let me box N2 gas. Product side. Where do I see an N2 gas here? Okay, I see an N2 gas here. That's good. Product side, product side. How about orange here? Orange, I have the CH2O. I have it on the product side. Here I have it on the reactant side. Not good. Okay, not good. Because here my target, it's on the product side, and the reaction they gave me, it's on the reactant side. Okay. So to me, okay, this is me when you're on the test and whatever, you're in the zone. Automatically for me, I'm going to flip reaction 3. Okay, so reverse reaction 3. So when I reverse reaction 3, it becomes CH4 liquid goes to CH2O gas plus H2 gas. And remember the rules of flipping. If something, when you flip it, the delta H now becomes the flip of the sign. So this is now minus 81.2 kilojoules, minus. All right. Here, you notice the N2 is on the product side, the 3H2 is on the product side. So I'm just going to add, without touching it, my second step here is that I'm going to add reaction 2 without doing a thing, not a single thing to it. So let's just add that here, add reaction 2. Okay, so that's going to be 2NH3 gas goes to N2 gas plus 3H2. Okay, I left it alone. I'm going to leave it alone, and that's going to be 55.5 kilojoules, 57.5 kilojoules. Now, what's my rationale for leaving it alone? My rationale for leaving it alone again is the N2 and 3H2. Okay, they're on the product side and my target. Okay, this is what I'm going to call the target. And I have here my CH4 on the reactant side. I have my CH4 on the reactant side, so that's also good. All right, N2H4. Okay, so N2H4, let's put this in blue here. N2H4 is on the reactant side. N2H4 here is on the product side. I'm going to reverse reaction 1. Okay, flipping reaction 1. This becomes N2H4. It, Thank you, sir.
I'll just set it right back here.
Yep. All right, reversing reaction 1. Okay, thank you, Alex, for that. Okay, reversing reaction 1, it's going to be N2H4 liquid plus H2 gas goes to 2NH3 gas. So I flip this. I flip this and I flip the sign. Now what's my rationale for flipping this? Okay, again here in my target it's on the reactant side, and by flipping it, reaction 1, I got it in my reactant side, which is what's in the target. So I flip this, flip reaction 1, it becomes minus 22.5 kilojoules. And then something nice happens when I do this. I mean, this is another thing in Hess's law. All right, so the circle here, the squiggly line here, okay, reactant, the little orange thing there, CH2O, that's the reactant, that's the product. And then N2 product, 3H2 product. Okay, and also guys see this? Do you see this, Hazel, Alex? You guys see that the 2NH3 here the 2NH3 here that's on the reactant side cancels out with the 2NH3 here that's on the product side. Okay, so this cancels and this cancels. So what am I left with? I'm left with N2H4. Okay. Oh, what else cancels? Hey, do you guys see the A hydrogen gas cancel? Do you see it, Elena? The hydrogen gas cancels also. So I have N2H4 liquid plus CH4O. Okay, plus CH2O gas. Okay, plus N2 gas. Everyone see this? Plus 3H2 gas. Okay, I got my target. Okay, I got my target. All right, this and this. So what's my delta H now? Okay, it's going to be minus 81.2 kilojoules plus 57.5 kilojoules plus a minus, which is a minus 22.5 kilojoules. Okay, so this plus this plus this gives me an answer of minus 46.2 kilojoules. And that is the answer. Okay, minus 46.2 kilojoules. It's still exothermic, right? So that's what a Hess's law problem is like. Okay, cancel out what you need to cancel out, and then we're left with our target, and this is our target. Add the corresponding enthalpy. So to get the target, we had a reverse reaction 3, leave reaction 2 alone, reverse reaction 1, add them up, cancel what needs to be canceled, add up the enthalpies. And that is a Hess's law problem. So the one in your lab is a little bit more difficult, so you can watch that and learn how to do that type of problem. But this is like on the level you'll see on an exam. All right, so that officially completes chapter 6. Now, with your permission, I am going to move on to chapter 7 because we want to finish the course. Okay, something totally new. Okay, something totally new with chapter 7, and that is quantum mechanics. There's actually a course here. Want this?
Oh, no, thank you.
There's actually a course offered in the department called quantum. So it's all about quantum mechanics. We're not going to go into that much detail here. This is what chapter 7 is all about. Okay. All right. First and foremost, I want to talk to you guys about electrons. So in our typical model of an atom, okay, we have the nucleus, which contains protons and neutrons, and sort of orbiting around it are electrons. Okay, they kind of buzz around the nucleus. Okay, it's these electrons that get exchanged in an ionic compound. It is these same electrons that get shared in a covalent compound. Okay? So here I'm going to make these electrons little orange dots. No. I'm going to make these electrons these little orange dots. Okay? Dots. Okay, dot. Okay, they're sort of orbiting, circulating around the nucleus, which contains protons and neutrons. Okay, however, I don't want you to think of electrons. I don't want you to think of electrons exclusively as these little dots, or I should say, I don't want you to think of these electrons exclusively as these particles. Okay, because these electrons can also be considered waves. Okay, have you heard of waves? Okay. I went to the beach 2 weekends ago. So what do you see in the beach? Okay, these waves. Okay. Waves. Okay. So an electron or electrons are not just particles, they are also waves. Okay, they display behavior of a wave. They display behavior of a particle. Okay, so electrons, a subatomic particle, have wave-particle duality. It's not a wave exclusively. It's not a particle exclusively. Okay, that's what makes quantum mechanics hard. It's the hardest math because you're trying to explain the mathematics of a wave and the mathematics of a particle. So they actually came up with a new math. It's called quantum mechanics and all the functions and all that stuff. So that's what we mean when we say wave-particle duality. Okay, light, which is basically a bunch of photons. Photons, okay, which are sort of, I want to call them electron packets. Has wave-particle duality. Electrons, which orbit the nucleus, have wave-particle duality. Okay? Are they a wave? Yes. Are they a particle? Yes. Are they both? Yes. Okay. The second thing I want to mention to you is this idea of quanta. Okay, whereas you want to consider photons, these little packets of electrons. Okay, a quanta has to do with a packet of electrons. Okay, a packet of energy. Actually, let me say this. A quanta is a packet of energy, discrete packet of energy. Packet of energy, that's a quanta. Okay, just like I bought chocolates for everyone. Just like this is a quanta of chocolate, this would be, think of this as a quanta of energy. Okay, energy. This does give you energy, right? I think you're having a bad day, you told me, so you can have something. Oh, you can have one. For everyone.
Should I pass?
No, that's all for
Oh, it's all for me?
you. You come get it after class.
Thanks.
Okay, quanta. Okay, I want you to think quanta now. All right. It's all for all of us. He just told me she's having a bad day, so that's all. Or not a great day. Okay, so there's a quanta. This is a packet. You agree? This is a packet of energy. Called a packet of chocolate, but we'll call it energy. So I want you to think of these packets as quanta. A packet is a quanta. Has anyone jogged stadiums? Stadium steps?
Yes.
You jog stadium steps? Jog stadiums? Okay. What happens when you jog a stadium? Okay, you have to be very careful that you don't trip and fall.
Yes.
Okay, you don't trip and fall. So let's say I put in some energy. Okay, I put in some energy to go up. And let's say that energy is, I don't know, I'm just throwing a number at you guys. Let's say that energy is 100 joules. Okay. I have to put 100 joules of energy to get to this second step. Okay, 100 joules, and I get on here. Okay. Now tell me, if I put 90 joules, if I exert myself 90 joules of energy, will I get on the second step? It takes 100 to get to the second step. Okay. But I'm only exerting 90. Will I get to the second step? No. Okay. Because I told you it takes 100. This is the key when it comes to a quanta, the packet. What if I put 101 joules of energy? If I exert 101 joules of energy, will I get to the second step? Yeah. More energy, I get to the second step. Quanta, packet of energy, will I get to the second step? No. 100 and 101. That is what a quanta is. Oh, I'm putting more. Okay, I'm putting 150. Oh, I put 200 input of energy now. I'll fall off. I'll fall off. I'll fall down. If I put 101, okay, I won't get on here. Okay. Well, you're telling me I'm putting more energy. I should be able to get here. This is where I want to go, right? No. Okay, that's what quantum mechanics is. Okay, that's the math involved. Okay, that is what the definition is of a quantum. That packet of energy and that packet of energy only. Okay? So stadium steps are a good example of a quanta. Okay? Don't think more is best. That amount of energy and nothing more, nothing less, right? So to get to here, maybe I need 2 quantas of energy to go from here to here, okay? I need 2 to get to here. Energy packet. Okay? What you guys are thinking, which is not what quantum mechanics, is that if I put 4 or 5, I should be able to get in. Okay? Maybe if I put another 2 more, I can get not to here, but to here. But I won't get to here. Okay? And that is what this quanta energy packet is. Okay? So the 2 main important points of this is electrons are waves and particles. And the way we consider them in terms of energy, because our last chapter was all on energy, the way we consider our energy is that these electron packets, these photon packets, this light packet, okay, they give off their energy in quanta, such that you need that much energy and that much energy alone. Okay, that's the idea of a quanta. Okay, think of your steps, or think of a packet of chocolates. Okay? Think of a packet of chocolates, or think of a step. You know, if I put more energy, I can't get to where I want to go. If I put less energy, you think I can get to the first step? Okay. No. Okay, let's say it gets 100 for me to get to here. Let's say, and again, I'm throwing out a number. Just throwing out a number. Let's say it takes 50 to get to this first step. If it takes 50 to get to this first step, that is how much I need, and that is how much I need alone. Okay, not 50.1, not 45, 50. Okay, this is 100. Okay, not 100.1, not 105, 100. 100 alone. That's how you need to think about this when you're thinking about quanta. And another thing you guys need to think about is you need to think both sides, that these electrons, these photons, whatever you're studying in this class for your homeworks, it's particles. Okay, think of a tennis ball. We can throw a tennis ball, we can move it around, but also think about it as a wave. Okay, let's talk about waves here. Okay, let's talk about waves. Okay, I want to talk about the anatomy of a wave. Okay, so a wave is an oscillating piece of energy. Oscillating back and forth, back and forth, back and forth. An oscillating piece of energy. So what are the parts of this wave? Okay. So if I were to take the top part of the wave, okay, the peak, and go to the next peak to peak, or what is that, trough to trough, low point to low point. Okay, high point to the next high point, low point to the next low point. I'm talking about wavelength. Wavelength has this Greek letter lambda. This is called lambda. That's the Greek letter lambda. And that's wavelength. All right, wavelength is a length. Wavelength is a length. Okay, so length, and the usual length is nanometers. Okay, so pretty small. Okay, your radio waves, your solar energy waves, the waves. Turn on the remote control. Okay, this laser pointer is a wave. And that distance is usually measured in nanometers. Okay. Another part of the wave, the point from where it reaches the high point, this is called the amplitude of the wave. Okay, the higher the amplitude, the higher the energy. Okay. And the final part of the wave is called the frequency. So imagine I'm standing here, or you're standing here. Okay. Remember, these things are oscillating and they're traveling. Okay, they're oscillating and they're traveling. So we're going to define frequency. Okay, it has the symbol V, cursive V. Okay, how many times the wave travels a point per second? Okay, so let's write that down. Frequency. How many times a wave travels a point per second? Okay. How many times does that wave? Remember, these things are traveling. Think of these ocean waves oscillating up and down, up and down, up and down. And they're passing some point. Here I'm having the wave pass through you or me. Okay? How many times does it pass through us? Per second. So the units here is going to be 1/second, and that is also called hertz. Hertz. Okay, hertz. Okay, 106.5, 96.5 megahertz on our radio dial. 101.5 rock on our FM radio dial. Hertz, okay, megahertz. Okay, those are radio waves. They travel in megahertz frequency. You can't see them, but you know, we can hear them. Okay. How many times it travels a point. So, let's look at this example here. All right, the wave is traveling, okay? And I'm just going to pick this point here. Okay. And I'll pick another point there. Okay, how many times do you think point A in wave number 1 passes this guy versus the same point A passes this guy? In other words, will A pass through this guy more times, or will A pass through more times here in wave 2? Which one, wave 1 or 2?
Pass through more in 2.
It will pass through more in 2, okay? It will pass through more in 2. Point A will pass through more in wave 2. Okay, so wave 2 has a higher frequency than wave 1 because it passes through the guy more. Okay, and then wave 1 here has the lower frequency. We can write that down. Lower frequency. This has a higher frequency. Okay, wave 2 has the higher frequency. What about the wavelength? Okay, pick top point to top point. Top point to top point. Which has the larger wavelength? Wave 1 or wave 2, Alex? 1 has the longer wavelength. Wave 2 has the lower wavelength. Right? Yeah. And wave 1 has the longer, or I should say higher, wavelength. I'll call it lambda. Okay, do we see this? Okay. So this brings us to another important point here. Okay, the wavelength and frequency of a wave, wavelength lambda, frequency v. Wavelength lambda of a wave, frequency v of a wave are inversely proportional. Are inversely proportional. Inversely proportional. As one goes up, the other must go down. As one goes up, the other must go down. Inverse. Okay? So wave 2, again, just want to remind you, wave 2 has the higher frequency. Wave 2 is going like this. And the lower wavelength. Okay, wave 1. Okay. Wave 1 has the longer wavelength and lower frequency. Wave 2 is like this. All right, when you multiply the wavelength and the frequency, okay, when you multiply that, you get the speed. Okay, speed. And, okay, here they're calling speed u, so I'll just call it u. Okay. Okay, don't forget, hertz is 1/second. A lot of people miss that. 1/second is hertz. So 360 hertz, as an example, is the same thing as 360 over seconds. Okay, cycles per second. Okay, hertz is 1/second. Okay, let's talk now about the electromagnetic spectrum. Okay, so there was an interview with the guy who founded Facebook, Mark Zuckerberg. And they asked him during this interview which scientist was the most, I guess, his inspiration, or which scientist was the most important in his career and all of that stuff. Okay. And he answered in the interview, the scientist that had most impact on the Facebook founder. The scientist that had the most impact on him was James Maxwell. Okay. James Maxwell. And not just the Facebook founder, but a lot of other people. I worked under a radiologist in my postdoc, and he really admired James Maxwell. And he wanted to give me a book on James Maxwell. Anyways, what was Maxwell most important for? Why do people love him so much, or why is he so important? His most important contribution was this, okay, the electromagnetic spectrum. Okay, his most important contribution was the electromagnetic spectrum. And the Facebook founder said, without this, there would be no Facebook, there would be no technology as we know it, there would be no whatever, okay? We'd have a very primitive civilization without Maxwell and him sort of elucidating the electromagnetic spectrum. Okay, so first, a couple of important points on the electromagnetic spectrum. So a lot of people miss this on exams, so I want to try to hopefully be successful this semester. The electromagnetic spectrum is actually two waves. That's the most important point one. It's actually two waves traveling perpendicularly to each other. Okay, one wave is the electric field wave. So I'm going to call that E with a little arrow above it. That means it's a vector. Okay, don't have to know that because you'll see it in physics class. Okay, and traveling perpendicularly to it, okay, at a 90-degree angle. Okay, at a 90-degree angle. Okay, 90-degree angle is the B field wave. Okay, the B field wave stands for the magnetic field. Okay, that little arrow over the B stands for magnetic field. Okay, so the electromagnetic spectrum is two waves traveling perpendicular to one another. A E field wave, electric field, and a magnetic field wave. So, important point number one. So know this for test, okay, a true-false test question, something like that. The electromagnetic spectrum is an electric field wave traveling perpendicular to a B field wave, okay? Magnetic field wave. Magnetic field wave. Okay, so that is what the electromagnetic spectrum is. They're traveling perpendicular to each one another, okay? Perpendicular. Okay, that's important point one. Okay, an electric field wave traveling perpendicular to a B field wave, they are mutually perpendicular to each other. And then the second important point about the electromagnetic spectrum is that it travels at the speed of light. Okay, the electromagnetic spectrum, all these waves that are part of the electromagnetic spectrum travel at the speed of light. The speed of light is 3 × 10⁸ meters per second. I'll give you that constant on the exam, but you should know they travel at the speed of light. Okay? Okay, all electromagnetic radiation, because this has energy, quanta of energy. all electromagnetic radiation travels at the speed of light. Okay, we're going to call that C, and C is a constant, and that constant is 3 times 10 to the 8 meters per second. So we get this equation here, where the wavelength of electromagnetic radiation times the frequency of that electromagnetic radiation equals C, which is speed of light. Okay. So 2 important points here. Okay, good short answer, good true false, multiple choice, whatever. So people can't see, you need to recognize that it's the electric field and magnetic field traveling perpendicular to each other. You'll probably get more of this in physics class, but that's what this is. This is what James Maxwell helped determine and construct. And here's the electromagnetic spectrum. Okay, I wish it was in color, but it's not in color, and it's blurry. But just want to get your attention to what all of this entails. Okay, this is why the Facebook founder was so keen on mentioning Maxwell. The electromagnetic spectrum consists of radio waves. So again, we can hear this. So this is more on the low energy scale, because FM waves and AM waves really don't harm us. What does harm us are right here, the high energy, the X-rays and the gamma rays. Okay. Notice the high energy is going to have a higher frequency. I'm going to call that V for frequency. And they'll have a very low wavelength. I'm going to call that lambda. Okay, that is what we associate with the high energy region of the electromagnetic spectrum. Obviously, X-rays are pretty powerful. Why are they powerful? I mean, literally, they could, how many of you had an X-ray done? No one here had an X-ray? Never went to the dentist? Okay, don't they put some lead thing around you in the dentist? Yeah, they don't want that X-ray to get to other parts of your body. In the old days, actually, this is true, before they didn't know how bad X-ray was when it was first discovered, and they would give it to cancer patients. They just zap them, thinking it would kill the cancer, but it would also kill the human, right? So the X-rays will have tremendous killing power. Okay, so that's part of the electromagnetic spectrum. Okay. Low energy, the radio waves. Here's something that we everyone's on their cell phone, so that's what is that? I can't even read that. Anyways, that's part of the electromagnetic spectrum. Microwave radiation. Okay, that's around here. Everything is kind of intermediary. UV. Okay, UV is bad for you because it's high energy, but also I don't know if you know this, UV will damage your DNA. Okay, it causes your DNA to clump. Okay, so that's why they ask for you to take sunscreen and they ask you to do all these other things. This is a pretty high, it's close to X-rays, right? Pretty close in terms of frequency and wavelength. So infrared is right here. The laser pointer, I'm pointing it at you guys, okay? Infrared is this thing here, okay? Infrared is the remote control on your TV set. And again, I'm sorry this is not in color, but there is a portion of the electromagnetic spectrum that we can hear. There's also a portion that we can see. Okay, we can see sight. and that's the visible region of the electromagnetic spectrum. So come to think about it, Maxwell was really amazing, if you come to think about it. Okay, visible. So there's a small slither. It's a very small slither. And they expanded it here. That is color. Okay, the visible region of the electromagnetic spectrum. Okay. And I believe it's Roy G. Biv, right? Roy G. Biv. And so we can see red, we can see orange, yellow, green, blue, indigo, violet. So this orange is actually, it's emitting waves. Yes, it's true, it's emitting waves that's being captured and processed by my eye. Okay, how do I know it's emitting waves? It's electromagnetic radiation that's in the visible region. Okay, it's just something we can see. Okay, this is radiation. Yes, it's radiation, it's energy, but it's not harming us. It's energy we can see. Visible region. There's energy we can hear, and then there's energy that can penetrate and get through skin and cells and all of that. A lot of biochemistry in here as well. Anyways, it's very fascinating, it's very interesting, and yeah, I really like this. Okay, it's really amazing. So low frequency end, we have, low wavelength end. We have the high wavelength end here, and then the low frequency end here. Okay, so the gamut, everything is in the middle, and even there's a small piece here that we can see. All right, very good. All right, let me also tell you about this photoelectric effect here. Just see where we are at here. What's a good stopping point? All right, let me now lecture to you guys about the photoelectric effect here. So our atoms, okay, I'm talking about an individual atom, has energy levels. All right, so if I'm going to put here energy on the y-axis, okay, energy levels. Okay, so we'll have energy level 1. Anybody play video games? Okay. The only guy plays video games. So video games, don't they have, in my time, do they have level 1, level 2, level 3? Okay. So inside the atom, we'll have energy level 1. Okay. And increase a little bit, we'll have energy level 2, energy level 3, okay, energy level 4. Okay, we can go on and on and on. Up to a certain point where we add so much energy that we will kick out an electron. Okay. That is when there's enough energy to just kick out the electron from the atom. So let's say I have an electron here. Okay, you just have to play along with me. I have an electron in the atom, and it's in energy level 1. We'll call that the ground state. Ground state. So what I'm going to do here is I'm going to hit it with energy, okay? Okay, I'm going to hit it with a quanta of energy. Okay, a quanta of energy. Sorry. Okay, a quanta of energy. Okay, I'm going to hit it with a quanta of energy HV. I'll talk about this later. Okay, a quanta of energy HV. V is frequency. Okay, and this electron, what happens if I hit it with a quanta of energy? Let's say if the quanta is just right. Remember, it has to be just right. Nothing more, nothing less. Remember. It takes 50 for me to get to here. Okay, not 51, not 100, not 200. 50 and 50 alone. So if I get it with the right quanta of energy, let's say I excite it to energy level 3. Okay, this is called excitation. Excitation. I've excited the electron. Now, did I kick it out of the atom? Okay, I did not kick it out. All I did was excite it from energy level 1 to energy level 3. I didn't kick it out. And I did that with the quanta of energy, HV. Okay, HV, a quanta of energy. And it's now moved, or it got excited from energy level 1 to energy level 2. Okay, this is what I'm talking about here. It's called the photoelectric effect. Okay, so what happens after something gets excited? What do you think generally happens? What happens after you get excited? What happens if a toddler gets excited and runs around? What eventually is going to happen?
Eventually die out.
Get tired?
Get tired, yeah.
Tired? Did you say die out?
Yeah, it's like the energy dies out.
Why do you say die? Well, we won't go that extreme and say die out. Get tired. What's another word for get tired?
Exhausted.
Exhausted. Here, the scientific word is relaxation. Okay, so after a while, after excitation, you hit it with a quanta of energy. It gets excited to some energy level. Okay, and then here I just gave it with that much packet. Okay, that much packet. This much packet of energy to go to energy level 3 within the atom. Within the atom. After a while, it will relax back to ground state. So we're going back down. We're going to call it relaxation. Relaxation. So it's going to relax back. As it relaxes back, what do you think happens? Okay, well, we gave it energy. It gets excited. It relaxes back. What will it do? It will give off energy. Okay, what will it give off energy as? It will give off energy. Okay, what will it give off energy as, though? It will give off energy that's somewhere in the electromagnetic spectrum. Okay? So the energy that it gives off, we're going to call that emission. Emission. Okay? So as it relaxes back to ground state, we have emission. So the photoelectric effect is excitation with a quanta. So here, going this way, we have excitation. Boom, 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 excitation. Excitation to a higher energy level, relaxes back to ground state. Or you can be morbid and say it dies off. It relaxes back to ground state. As it relaxes back, it emits energy. Okay, what form of energy does it emit? Okay, it could emit light, red light, white light, blue light. It could emit infrared. It could emit, microwave, whatever, somewhere here in the electromagnetic spectrum. So that is what the photoelectric effect is. All right? In fact, I think we have it here. Okay, if you look here, these are all the emission spectra, emission of all the elements of the periodic table. Okay, so somewhere, somehow, they hit it with enough quanta that it excites, and then it relaxes. As it relaxes, this is emission in the visible region, Roy G. Biv. This is emission in the visible region of the electromagnetic spectrum. All right, so that is the photoelectric effect. Okay, excitation, relaxation back to ground state. As it relaxes, it emits. So for an excitation, there's emission. I want to tell you a little bit about this equation here. I think I already told you about this. Okay, electromagnetic radiation travel at the speed of light, and its magnetic field wave traveling perpendicular to electric field wave energy. Okay, all of these have energies. Okay, obviously, if you had an X-ray, you know you had energy. And some of these you don't feel the energy. Some of these you see the energy. And the energy in the electromagnetic spectrum, whatever you're talking about, UV, IR, UV, radio, X-ray, okay, whatever you're talking about is E equals H times frequency. Okay, this H is Planck's constant. Okay, I'll give you Planck's constant, and Planck's constant, again, I'll give this to you on the exam. It's 6.63 times 10 to the minus 34 joules times second. Okay, and I'll give that to you on the exam. Okay, so do not memorize it. And then V is the frequency. Okay, what are the units of frequency? Okay, hertz. Okay, I want you guys to know units of frequency is hertz. What is hertz? I want you guys to know that hertz is the same thing as 1 over second. By the way, we know that these travel at the speed of light, right? Which another constant that I will give you, 3 times 10 to the 8 meters per second, speed of light. So I can do a little bit of math here. If V equals to C over lambda, I can substitute that C over lambda here. Do you guys see where I'm getting at in all this math? Algebra. And another way to express this equation is E equals HC over lambda. Okay. Which is a mistake on your notes, which I apologize. But so E equals HC over lambda. I'll give you both equations on the test, so not something that you need to memorize. Let's do a practice problem here really quickly here. All right, the energy of a photon is 5.87 times 10 to the minus 20 joules. Okay, notice here energy is in joules. Okay, what is the wavelength in nanometers? Now let's step back for a second here. Okay, I want all of us to step back and think about this. Okay, What did we say about a photon? Is it a particle, or is it like a, isn't it like a particle, light particle? Okay. Yeah. Photon is a light particle. There's an energy of that electromagnetic radiation. What are we being asked to solve? Wavelength. Wait a minute. How can you solve for the wavelength? Wavelength is waves, is it not? Is this not correct? Wavelength is waves, but a photon is a particle. Okay, right? So that's the wave-particle duality. These things, these electrons, this light, all these things are wave and particle. Part wave, part particle. They display and exhibit behavior that's reminiscent of a wave and have a wavelength. And they display behavior that is reminiscent of a particle. That is, they orbit the nucleus. So what is the wavelength in nanometers? All right, so energy is equal to hv. Okay. And we know that these things travel at the speed of light. So they ask for the wavelength, right? So wavelength is equal to c over v. Right, here the energy is 5.87 times 10 to the minus 20 joules. Okay. That divided by Planck's constant. Okay, Planck's constant is something I will give you in the test. Do not memorize it. 6.63 times 10 to the minus 34 joules times second. So solving for frequency v, we have energy over Planck's constant. We have a calculator here. I don't think I have a calculator. Do you have one, Alex?
Yeah.
Can you do this math quick? 5.87 times 10 to the minus 20.
Oh,
5.87 times 10 to the minus 20. Divided by 6.63 times 10 to the minus 34.
So I got 8.85 times 10 to the negative 55.
Minus 55 hertz. Okay, that's 1 over second. All right, so this over this is 8.85 times 10 to the minus 55 hertz. Okay, that's our v. Okay, we know c is our speed of light. That's 3 times 10 to the 8 meters per second. Meters per second. Divided by v. V is 8.85 times 10 to the minus 55 hertz. Hertz is 1 over second. So the second cancels and we're left with meters. So one more calculation, Alex, please. 3 times 10 to the 8th. 3 followed by 8 zeros. 3 times 10 to the 8th. Divided by parentheses. 8.85 times 10 to the minus 55. Close the parentheses.
I got 3.39 times 10 to the 60
this divided by that.
That's what I got. Okay, let me redo it again.
3 times 10 to the 8th divided by parentheses 8.85 times 10 to the minus 55. Close parentheses.
Okay. 3.39 times 10 to the negative 48. Does that seem more right to you?
Negative 48 meters. Okay. I'm not sure, but all right. All right, 3.39 times 10 to the minus 48 meters. And then we want to convert that to nanometers. So 3.39 times 10 to the minus 48 meters. To convert it to nanometers, okay, this is the conversion that you will use. 1 nanometer is 1 times 10 to the minus 9 meters. Okay, that's the conversion factor. And actually what I need to do is flip it to get the meters to cancel out. So to get this to nanometers, it's going to be 3.39 times 10 to the minus 48 meters times 1. Oh, this is right. 1 nanometer is 1 times 10 to the minus 9 meters. Yeah, the meters cancel. Okay. So take this number and divide it by 1 times 10 to the minus 9 to get it in nanometers. Can you do that? 3.39 times 10 to the minus 48.
You said 3.39.
Just converting the meters you gave me to nanometers. Okay, divided by 1 times 10 to the minus 9 to get it in nanometers.
To the negative 9?
Yep, 1 nanometer is 1 times 10 to the minus 9 meters. That's something you guys should know
Right, so
for your conversions.
This is 3.39 times 10 to the negative 57.
You divided it?
Let me redo it again.
So usually if you flip it 10 to the minus 40, it should be 39. It should be minus 39, I think, nanometers.
Right, 3.39 times 10 to the negative 39.
Yeah, it should be minus 39 nanometers. Okay? So this is how you do that problem. So regardless, with the calculations, E equals HV, solve for frequency, put the frequency in here, and speed of light divided by the frequency gives you the wavelength. To get it from meters to nanometers, you're going to have to divide it by 10 to the minus 9, because 1 nanometer is 10 to the minus 9 meters. So something that's a particle, we're calculating a wavelength. A particle has a property of a wave, such as a wavelength and a frequency. So that's what this whole quantum mechanics thing is all about. All right, on next week, I'm going to talk about electron configuration. So check out whatever videos I have on Canvas. I'll try to upload some more this weekend. And thank you for coming. Have a good day. And please take this bounty of chocolates. Maybe this will make your day better. Or will get rid of your chemistry headache. It's here. Can I give you some, Alex?
Sure, I'll gladly take some. Thank you so much.
Take more. I think we have lab next, so I'll see you at 2 o'clock. All right?